Welcome students. Today we are going to discuss about electrophilic aromatic substitution reaction. To discuss about this is a characteristic reaction shown by benzene. Characteristic reaction means that this reaction is shown by in whole of the organic compounds. This reaction is shown by benzene and its derivatives. To study more about electrophilic aromatic substitution reaction, we need to draw the structure of benzene on the board. So here we have the structure of benzene. Okay. As you can see that there are 3 double bonds in the benzene ring. 3 double bonds means that the benzene ring has 6 pi electrons. So it is a electron rich compound, it is a electron rich species. Now if you are putting an electrophile in this system, what the electrophile would tend to do? It would try to attack the benzene ring. So here I am putting an electrophile. Now there can be 3 cases. It can try to attack from this position, it can try to attack from this position, or it can try to attack from the third position. Now if the electrophile attacks from the first approach, then immediately at the next moment this double bond would shift to here. In the similar case, if it attacks from second position, this double bond will shift here. And in the third case, if this attacks from the third position, it would shift here. So you will get a second structure of benzene like this. It would be like this. Yes. So and now if the electrophile attacks at this position, it would again go at this one. If the electrophile goes and attacks this, it would again shift. If this attacks at this position, it would again shift to this position. So this structure would come. So when it attacks from this at this structure comes, and when it attacks at this structure would come. So you can say that the structure, the 6 pi electrons in the benzene ring, it is in random or it is in dynamic motion. The 3 double bonds, the 6 pi electrons are at random motion inside the benzene ring. Dear students, you can compare it when you switch on the fan. Okay, when you switch on the fan, the blade of the fan is at random position. You can't spot the position of a blade of the fan. Can you spot it? It's not possible. So the overall structure of that fan in motion is the combination of all the motions. Correct? The overall structure would be a combination of all the dynamic positions of the blades of the fan. Similarly, the overall structure of the benzene would be a combination of these 2 structures. That is, we get a structure like this. Right? This is a resonance hybrid structure of the benzene ring. These are the canonical forms of the benzene ring, and this is the overall resonance hybrid structure of the benzene ring. Okay, this delocalization of the electron is referred to as the resonance. Okay, and this is the resonance hybrid structure of the benzene ring. So overall, you can, for simplicity, you can draw a hexagonal structure and you can represent this delocalization by a circle inside this hexagonal structure. Now coming back to our electrophile, the electrophile is trying to catch an electron pair from the benzene ring, but it is unable to do so because the electron pair is in resonance. The 6 electron pair is in resonance. It is unable to do so. This makes the benzene ring very unreactive because the electrophile is not able to catch the electron pair. Therefore this makes the benzene ring very stable. So you can say that delocalization of electrons, of 6 pi electrons, makes the benzene ring very stable. What is delocalization called? Resonance. So the resonance in benzene ring makes that benzene ring very stable, and such kind of stabilization is referred to as the resonance stabilization. So it's the resonance stabilization which makes the benzene ring very stable, and because of resonance stabilization, E plus do not undergo any addition reaction to benzene ring. So what other option does E plus have? Let us see. The benzene ring actually has 6 carbon atoms and 6 hydrogen atoms are attached to it. So the E plus or the electrophile has another option. What the benzene ring does is replace one of its H plus. The H plus will go to base, a Lewis base, and substitute that H plus with E plus. In that case, both the conditions of E and benzene ring are satisfied. The E gets its electron pair. When H plus goes, it gets its electron pair, and also the benzene doesn't lose its 6 pi electron. The benzene doesn't has to partake with its delocalization of electron, or doesn't have to partake with its resonance stabilization. The resonance stabilization of the benzene ring is also maintained. The E plus also gets its electron pair. So overall it's a win-win situation for both of them. Such reaction are referred to as electrophilic aromatic substitution reaction. Electrophilic because the electrophile started all this problem. Aromatic, right, it is occurring in the aromatic ring. And substitution because H plus has been substituted by E plus. Therefore electrophilic aromatic substitution reaction. Dear students, now we will see the steps in electrophilic aromatic substitution reaction. Let us see. Let me rub the board. Now we will see the steps in electrophilic aromatic substitution. There are 3 steps. Step number 1. Who is the problem maker here? The electrophile. In each cinema, normally the problem maker is villain. The villain has to come from somewhere in the scene. Similarly, here also the electrophile has to come from somewhere. So the step 1 is the formation of electrophile. Formation of electrophile. Formation of E plus. How can it be formed? There are 2 steps. The first is spontaneously. It can form spontaneous dissociation. In this, you can say that a reagent, an unsymmetric reagent, it can dissociate into E plus and Nu minus. In the other case, acid catalyzed dissociation. In that case, you need a Lewis acid, La. It can react with this reagent, and the Lewis acid can get its nucleophile and electrophile will be formed. So this is the step 1, formation of electrophile. Any unsymmetric reagent, a polar unsymmetric reagent, the bond should be polar here, and ample dipole moment should exist between the positive addendum and the negative addendum. If such is the case, then it can split, it can dissociate by its own. E plus can be formed in this way, or otherwise we need an external reagent. If there is no ample dipole moment between them, we need an external reagent. So we can use a Lewis acid. Now Lewis acid has an empty d orbital, so it can accept a pair of electrons from nucleophile. Here it accepts and the electrophile has taken birth. So in both cases electrophile takes birth. Now it is the time that electrophile attacks the benzene ring and forms a carbocation. So we go to the second step, formation of carbocation. Let me rub the board to show you that step. Step 2, formation of carbocation. Formation of carbocation. Okay, so what happens in this step? The E plus now tries to attack the benzene ring. And what structure would result? Suppose if it attacks at this position, that is if it takes this electron pair, then what would come out? These two bonds, nothing happens to them. This electron pair has been taken. There is E and here it is H. Now when it takes this electron pair, it actually takes electron from this carbon. This carbon's electron is already there. This electron has been taken and given to E. So who is at loss? Yes, absolutely right. This carbon is at loss. Now what would happen? This electron pair, to compensate for the loss, this electron pair would jump here and we get a second structure. And that second structure, nothing happens here. This pair jumps here. You write the E and H. If this electron pair jumps here, nothing would happen to this carbon atom. The electron has been actually taken from this carbon atom, so the positive sign will come here. Now in the third way, to compensate for this loss, this electron pair would jump here and we get a third structure which is something like this, right? And EH. So positive sign will come here because the electron from here has come to here. Okay, so nothing has happened to this carbon atom. The positive sign would come here. Now overall, if you draw the resonance hybrid structure of this would be like this. EH will be here and positive sign is just getting rotated inside the benzene ring. So the positive sign is getting rotated. It's overall positive. You can see positive sign rotating, and here we have represented as a resonance hybrid structure. This is a very unstable condition, not natural, because benzene should have 6 pi electron. So this is an unstable condition. How to relieve this unstable condition? That we can study in step 3. So this is the step 2 where carbocation formation is there. Let us now go to step 3 and study how it relieves this condition. Step 3, abstraction of photon by base. Step 3, abstraction of proton. Abstraction of proton by base H plus. Okay, by base, Lewis base, of course. Now what would happen? Let us draw our carbocation. Overall, you know it's positive. Here it is E, here it is H. Now base is there. Pardon for the, yes, base is there. Now what would happen? This electron pair, it would come here into the system and H would go and attach itself to the base. So everything is solved now. When this electron pair comes inside, it would, the 6 pi electrons are restored. E remains here and the base would go with hydrogen. Hydrogen would go with base. So here we go. We got the electrophilic substituted benzene ring. So these are the 3 steps of electrophilic aromatic substitution reaction. What are the examples? There are 5 examples. 5 examples of such reaction which we study. Number 1, you go for, number 1 is bromination. Number 2 is nitration. Number 3 is sulfonation. Number 4 is Friedel-Crafts alkylation. And number 5 is Friedel-Crafts acylation. So these are 5 examples of electrophilic aromatic substitution reaction that is shown by the benzene ring: bromination, nitration, sulfonation, Friedel-Crafts alkylation and Friedel-Crafts acylation. These reactions we will see in separate videos with its mechanism. If you like the class, do subscribe the channel. Thank you very much.